Hi, I'm Rebecca. During this lesson, we're going to look at working with trigonometric identities. Let's look at the specific objectives now. We want to simplify trigonometric expressions and look at verification of identities. Let's begin with our first example. We're going to be asked to simplify the following expression. Here we have sine squared x times cosine x times cosecant cubed x times secant x. In order to work with this expression, what we're going to begin by doing is changing each of these terms to something in terms of sine or cosine. So we can begin by just rewriting the first two. We have sine squared x multiplied times cosine x. Now, instead of writing cosecant cubed x, we're going to think of that as 1 divided by sine cubed x, using the reciprocal identity. Likewise, when we look at secant x, we'll use a reciprocal identity also, and we're going to write that as 1 divided by cosine x. Now, the next thing that we're going to do is think about these first two terms. You can think of them as being over 1. And that way, it's easy to see that here we have some terms in the numerator. These are factors of the numerator if we multiplied this all together. And here we have a factorization of a denominator. We're going to now end up undoing any common factors that we have between numerator and denominator. For instance, you may note that we have a cosine of x as a factor of both the numerator and denominator. We can divide the numerator by the cosine of x, and that's going to give us a 1 here. Divide the denominator by cosine x, that also gives us a 1. We also note that we have sine squared x in the numerator, sine cubed x in the denominator. We can divide numerator by sine squared x to give 1. We can divide denominator by sine squared x. Sine cubed x over sine squared x would give us simply sine of x. Next then, notice we can multiply our numerators together, yielding a numerator of 1. We can multiply these four denominators, 1 times sine of x times 1, which gives sine of x. And using a reciprocal identity, we can recognize that 1 divided by the sine of x is equivalent to the cosecant of x. Let's now try another example. Here, what we'd like to do is to factor the expression that's given. In our first part of this problem, we're going to be looking at secant squared theta minus 1. Now, when we look at this, what we want to recognize is we only have two terms. There are no common factors. That we can notice that we have a first term squared minus a second term, which can also be thought of as a perfect square. If you recall this algebraic formula, we have the difference of two squares, a squared minus b squared. Recall that that can be factored as a minus b times a plus b. Using that idea, what we're going to see is that we can rewrite this as the secant of theta minus 1 times the secant of theta plus 1. Now, we also want to try to do the same type of problem, only this time our example is going to be to take 2 times the sine squared t minus the sine of t minus 1, and we want to factor that. Here we have three different terms. Notice that in our first term we have sine squared. In our second term we simply have sine, and then we have a constant. This should resemble for you a quadratic format. In order to factor this, we're going to think of taking the first term and breaking it up into two factors. That is, we can rewrite this as 2 times the sine of t in the first of our pair of parentheses and the sine of t in the second. Notice that here we have this multiplication giving us back our first term. Now, we're going to next look at our last term, which is a 1. And notice the only factorization we have here is 1 times 1 that we can use. And so we're going to end up now thinking of that FOIL method. Recall you have the first times the outer times the inner times the last. We've taken care of the first, giving us that first term. We have the two last terms here, giving us the last one in our original expression. And now we want to make sure that we end up with a negative sine t or a minus sine t in the middle. To do that, what we have to notice is that our middle terms would give us a product of sine t. Our last terms would give us a product of 2 times the sine of t. We need to combine these inner and outer terms in order to come up with a negative sine of t. To accomplish that, we'd need a minus 2 sine t plus 1 sine t. And so if we put a plus sign in our first set of parentheses and a minus sign in our second set of parentheses, then we end up with the correct factorization. Let's now try another example. And here we want to simplify the following problem. Let's look at 3 times the sine of theta plus 6 divided by sine squared theta minus 4. In our numerator, you notice we have 2 terms, and there is a common factor. We can think of this as being equal to 3 times the sine of theta plus 2. In our denominator, you'll notice that we end up having, again, a difference of 2 squares. We can think of this as sine of theta and then minus 2 times sine of theta and then plus 2. And now notice that we have a common factor of sine of theta plus 2. And so we can actually think of dividing both numerator and denominator by that term. It divides out. And we come up with 3 divided by the sine of theta minus 2. Now we want to move on to verifying some identities. And what's going to happen when we verify an identity is that we're going to end up with what looks like an equation. What we're trying to show is that one side of the equation is equivalent to the other side of the equation. What happens in this particular example is you'll notice that we can't use properties of equality because we don't really know that this is equal. We're being asked to verify that these two things are equivalent. So for instance, be cautious here. You can't decide to multiply both sides of this equation by the denominator, for instance, because that's a property of equality, which means that we would have to know they were equal to start with. What occurs instead is usually we start with one side of the equation and try to work it to where we see it's equivalent to the other side of the equation. Let's now begin this particular example by starting with this side of the equation, which has a fraction in it. We're going to have 1 divided by the sine of theta minus the sine of theta. And what I'm going to do is try to transform it somewhat. One thing I notice is that I have a fraction here and I don't have a fraction here. What we could do is combine these terms by getting a common denominator. So what you may note is I can think of this as being over 1 right now. The common denominator would be sine of theta. We're going to rewrite our first term, leaving it as is. In our second term, we want to come up with an equivalent fraction, which is going to have a denominator of sine of theta. Notice you can think of this as 1 times sine of theta gives me this denominator. So multiplying the numerator also by sine of theta would give us sine squared theta. Now, once we have the same denominator, then we know we can combine numerators. So we'll have 1 minus sine squared theta divided by sine of theta. Next, what I can do is look at the numerator in terms of Pythagorean identities. Recall that we know that cosine squared theta plus sine squared theta equals 1. So cosine squared theta is equivalent to 1 minus sine squared theta. Let's substitute into our numerator, replacing 1 minus sine squared theta by cosine squared theta. Now, we've come up with the expression at this point, and what we can notice is that it can be simplified somewhat further if we do a little bit of manipulation with these terms. Let's continue now. What I'm going to do is rewrite where we were in the problem. We had cosine squared theta divided by sine of theta. And what I think I want to do is break this squaring up. Let's think of that as cosine of theta multiplied times cosine of theta. Now that's being divided by the sine of theta, but I'm going to think of this as sine of theta times 1. And the reason for doing that is I now can separate this into 2 fractions. The first one I can write as cosine theta over sine theta. The second one I can simply rewrite as cosine of theta over 1. Simplifying further, the quotient identity can be used here in order to rewrite this first cosine theta over sine theta, as cotangent theta. And in the second case, what we notice is we have simply cosine theta. So we're able to rewrite this expression so that we don't have a fraction and we don't have a trigonometric function squared. And so this is considered a simpler version of the problem. Now, let's verify that what we came up with is actually where we wanted to be. If we look back, we came up with cotangent theta times cosine theta. Let's look back at what we were being asked to do. We were asked to verify that indeed this expression was equivalent to that. And so you can see that we've come up with the solution as was asked for. Now let's try another problem where we're going to be working with a verification. Here we want to verify that cosine of t times tangent of t minus secant t is equivalent to sine of t minus 1. Now, when you're working with these verifications, most of the time what occurs is you want to start with what looks to be the harder side of the equation. And that is the one that really at least gives you somewhere to start working on. And what I notice is that this side of the equation, I kind of have an idea of what to do with this. That is, I know at least I can change everything in terms of sine and cosine instead of having 3 different trigonometric functions. On the right-hand side of the equation, I really don't even know where to go with this expression. That is, there's nothing that jumps out at me as to how to simplify it. So I'm certainly going to start with the left-hand side of the equation in trying to do this verification. Let's then begin by rewriting the terms inside the parentheses so that they're in terms of sine and cosine. So we're going to have the tangent of t rewritten as sine of t divided by cosine of t. We're going to have the secant of t rewritten as 1 over cosine of t. And now notice that I could go ahead and simplify inside the parentheses if I'd like. That is, I can rewrite this as cosine of t multiplied times the fraction sine of t minus 1 over cosine of t. Next, we can multiply by cosine t, and notice that this ends up being a common factor to the numerator and denominator, so we can cancel that common factor. And we come up with sine of t minus 1, which is where we were trying to go. Now next, it's your turn to try to do a problem on your own. We want you to stop the tape as you try the problem, and then we'll come back and work it together to see how you did. Here's what you'd like to work on. Verify that sine of theta divided by cosecant theta plus cosine theta divided by secant theta is equal to 1. Let's begin by looking at the left-hand side of this equation, which certainly is the more difficult side of the equation to work with. We're going to start by noticing that we can rewrite all of the terms here in terms of sine and cosine. Now, our numerator remains sine of theta. We're going to have our denominator rewritten as the reciprocal of sine of theta. Add that to the fraction where the numerator remains cosine theta. The denominator becomes 1 over cosine theta, since secant is the reciprocal of cosine. Now next, what we need to do is to simplify each of these complex fractions. What we notice is that in order to simplify the first one, I would need to multiply the denominator by sine of theta. But of course, that's going to require me to multiply the numerator by sine of theta also. In the denominator, the sine of theta will end up canceling out, and I'll end up simply with sine squared theta. We'll do something similar in our second complex fraction. Here we'll multiply by cosine of theta in both numerator and denominator. Again, cosine theta ends up canceling out, and we end up with cosine squared theta for our second term. And now this should be recognizable as being equivalent to the value of 1. So we have sine squared theta plus cosine squared theta, that is equivalent to 1. And that's the identity that we were being asked to verify. And we're going to move right along into another verification problem to show you some other techniques. Let's verify that the sine of A plus the cosine of A is equal to sine of A divided by 1 minus cotangent A minus the cosine of A divided by tangent A minus 1. Again, it's not very hard to pick out the tougher side of this equation. And so we're going to look at the side that's to the right and try to show that it actually is equivalent to the side to the left. Let's begin again by taking these expressions and writing them in terms of sine and cosine. Many times when you have at least more than two trig functions involved, that's typically going to be the technique you're going to use. We're going to rewrite cotangent as cosine of A divided by sine of A. We're going to rewrite in the denominator the tangent of A as sine of A divided by cosine of A. And next, what we're going to do is, again, try to work with these complex fractions individually. In the complex fraction to the left, I'll note that I'll need to multiply both numerator and denominator by sine of A. That will yield sine squared A divided by, we're going to multiply the 1 times the sine of A, and we'll multiply that fraction times the sine of A, leaving us with a 1. With a cosine of A. And then let's multiply in the second fraction. This time we're going to try to get rid of this denominator, which is cosine of A. So we'll multiply every term here by cosine A. We'll end up with cosine squared A divided by, our first term, the cosine A will cancel out, leaving us with sine of A. And we'll multiply a 1 times cosine A. Now this problem works out nicely because we can see that we end up with now a common denominator, and therefore we're going to now work further on the problem. And what we're going to do is notice that since we have a common denominator, we can rewrite this with that denominator, sine of A minus cosine A. The numerator becomes sine squared A minus cosine squared A. Here again, we have a difference of two squares, and we're going to factor that difference of two squares as follows. We'll have sine of A minus cosine of A times sine of A plus cosine of A. And in our denominator, we have our sine of A minus cosine of A. Again, we note that we have a common factor. We can divide out the common factor, leaving us with sine of A plus cosine of A. Now, sine of A plus cosine of A, let's refer back to the problem that we started with, because that's what we were trying to verify. We started with the right-hand side of the equation, and recall that we worked it down to this format. And so therefore, we were able to verify the problem that was given to us. And now we're going to do yet another example. In this problem, we're going to be looking at verifying that secant alpha minus tangent alpha squared is equal to 1 minus sine alpha divided by 1 plus sine alpha. Now, even though it may not be obvious to you what would be considered the harder side of the equation right now, I mean, one of them has it squared and the other one's a fraction, if you think about it, I'm not real sure exactly what to do with this side. And so, at least on this side, it's indicated that I should square everything that's being given here. So I'm going to go ahead and do that now. I'm going to multiply out. Now, remember that this side of the equation actually means that what you're looking at is the secant of alpha minus the tangent of alpha multiplied times another secant of alpha minus the tangent of alpha. Now, you can write it out in this format and then use FOIL method if you'd like. Or, if you know the formula for a minus b squared, you could do it in that manner. Either way, what we come up with is secant squared alpha minus 2 times the secant of alpha times the tangent of alpha minus, plus, because we have a negative times a negative, plus the tangent squared of alpha. Next, what I need to do is remember that we're trying to get to this format, and so therefore we notice we have everything in terms of sine over here. One way to get there is to change all of these terms again in terms of sine and cosine, and then simplify. We're going to rewrite secant squared alpha as 1 divided by cosine squared alpha minus 2 times secant alpha is the same as the reciprocal of cosine. Tangent of alpha is the same as sine alpha divided by cosine alpha. And then we have as our last term tangent squared alpha, which can be rewritten as sine squared alpha divided by cosine squared alpha. Now let's continue on with this problem where what we're going to try to do is to combine our terms by noting that we have actually common denominators. Let me go ahead and do a middle step here before I do that, just to point out what we're working with. I'm going to go ahead and combine all these terms in the middle, or these three factors, that is. We're going to have 2 times the sine of alpha divided by cosine squared alpha. And then we have in our last term, just rewriting it, of sine squared alpha divided by cosine squared alpha. So again, what we note is that we do actually end up with the same denominator in all 3 terms. Let's now continue, and what we're going to do is work with combining these numerators. We're going to have 1 minus 2 times the sine of alpha plus sine squared alpha, and we're dividing that by our common denominator of cosine squared alpha. Now at this point, you may note that we have a numerator which appears to be of the quadratic form, and that makes us think about factoring. The other thing that we may notice is that our denominator is cosine squared alpha, but remember that we're trying to end up with a term, with terms that only have sine in them. So therefore, what we probably want to do is go to a Pythagorean identity where we can rewrite cosine squared alpha in terms of sine squared alpha. So we're going to look at this in 2 steps. We're going to first of all notice that I'm just going to rewrite the numerator for the first step. And in my denominator, I'm going to use the Pythagorean identity, which tells us that we can rewrite cosine squared alpha as 1 minus sine squared alpha. Now I'm going to factor both the numerator and the denominator. In my numerator, I'll think about it in that FOIL type method. Notice that we have a 1, which can be rewritten as 1 times 1. My last term is sine squared alpha. That can be factored as sine of alpha times sine of alpha. And notice that in order to come up with a middle term of negative 2 sine alpha, I'll need to have a negative sign in both of those factors. In my denominator, I notice that I again have a difference of 2 squares. That's going to be 1 minus the sine of alpha times 1 plus the sine of alpha. And we have our common factor, which can be divided out, to come up with 1 minus sine of alpha divided by 1 plus sine of alpha. Let's just go back to the original problem and make sure that we did indeed come up with what we were being asked to work with. And sure enough, here we are at the format that we were being asked to work toward. So we note that we can rewrite this expression in this format. Now, in this particular lesson, we've done quite a few problems where we were working with trigonometric identities, and we were doing this in order to simplify expressions and to verify some other trigonometric identities. It's time now for you to devote some time to doing these problems on your own. Make sure you review as you go the different identities that we can be working with and the different techniques that we've reviewed. Try some problems now.